Hey guys, welcome to section C and D of chapter 6. We're going to keep talking about earthquakes. So earthquakes need to be measured. In order to know how strong they are, we need to be able to measure them. And there's different devices to do that. We talked about seismometer. That is the actual device that measures those seismic waves. Okay, but we've got some other terms that go along with that. A seismograph is a seismometer with a recording system, which I don't know why you'd ever have a seismometer without the ability to actually record the results, but I guess there is. Okay, so a seismograph records that. A seismogram is the actual recording. Okay, so with that picture there, that little those lines. Let me get my pen. Okay, that would be the seismogram. Okay. So it used to be that these old seismometers were actually fixed to the bedrock of the earth. Okay, it was a frame, and it held like a hanging mass. Okay, so you can kind of think of something just hanging from a string. Okay, but it's connected to this frame, and so if the earth moved, it's going to move the frame, right? And then that mass is going to swing back and forth. Well, oftentimes there was like a pen on the bottom of it. Okay, and as it would move, it would literally write on a piece of paper. Those are the early, most primitive forms of seismometers. They've gotten way more advanced and more technological and use computers and things like that. But the same principle is still there. It's a unit that is on the ground. And as the ground moves, it shakes. And so it records that shaking. So the more movement there is, the higher these lines are going to be. Okay. If there's only a little shaking, the pen's only going to move a little bit. If there's a lot of shaking, the pen's going to move a lot. Okay. And so that's how you measure earthquakes. What we're actually measuring are these seismic waves. Okay. And there's two main types of seismic waves. There's body waves and there's surface waves. The body waves move underground. They move in the body of the earth, whereas the surface waves are up at the top. Now, there's two main types of body waves we talk about. There's the P waves. The P is for primary, so that's the first seismic wave that goes. Okay, and it's able to travel through both solids and liquids. Remember, there's molten material underground, and so it's able to travel through both the solid rock and the molten rock. The second wave, or the S wave, S for second, is stronger than the P waves, but slower. But they can only pass through solids, okay, not the molten material. And then finally, we get the S waves. They're the last waves that come. And so as these P waves and S waves are moving, they're getting closer to the surface. Once those seismic waves hit the surface, they're known as surface waves. And that's the waves that cause most of the damage because that's where everything is. They travel along the surface, and that's why buildings collapse and things like that. Okay, so you need to know those three types of seismic waves. Got some other vocab that goes along with earthquakes. We need to know where the earthquake occurs. Okay, so the focus is the actual underground location. Okay, so this is where that stress would finally cause the faults to slip. Okay, wherever that occurs underground, that's known as the focus of the earthquake. But you've probably heard the term epicenter before. That is the place on the surface directly above the focus. Okay. And so, people are up here, they're concerned with what's happening on the surface. So the closer you are to the epicenter, obviously, the more you're going to feel that earthquake. Okay. So in order to determine the epicenter of an earthquake, we need to do something known as triangulation. And basically, you need three locations. You need three seismometers to calculate how far away the seismic waves are coming from. Okay, because if you had, so here's a seismograph there, here's a seismometer there, and if you've got these, that's a horrible one there. If you've got these two different locations that are measuring the time it takes for the seismic waves to hit, if you only have two, you've got two locations that this could possibly be. Okay, so you need a third seismometer to triangulate. And so the place where all three overlap tells you where the epicenter is. And actually, if you look at page 140 in your book, there's a much better picture of that. There's a map, and it kind of explains how that triangulation occurs. Okay. And then it's important to know that most earthquakes happen along those plate boundaries. I have a typo there, plate. Let me fix that. Boop, perfect. They most frequently occur along those convergent, divergent, and transform plate boundaries. And that should make sense. Where those boundaries are, those tectonic plates are going to be moving. And so it stands to reason that there would be the most earthquakes there. That's also where the most volcanoes occur. And we'll talk about that, I think, next chapter. All right. When we talk about how strong an earthquake is, we refer to its magnitude. And the most common scale for an earthquake's magnitude is the Richter scale. But the Richter scale is not a linear scale. So if you have a magnitude of 5, that doesn't mean it's 1 time stronger than a magnitude of 4. Okay. Each unit means that it's 31.6 times more energy. So magnitude 1 is whatever. Magnitude 2 is 31.6 times stronger than that. And then there's, decimal points. You can have a 3.5, you can have a 6.7, so it's kind of a hard scale to really understand what it means. Diagrams like this kind of break it down. The number 6 is a pretty significant earthquake, 6 and higher. 7 would be considered a major earthquake causing serious damage, and 8 would be kind of catastrophic. Okay, and that's just like whole communities are going to collapse. Okay. Again, the magnitude indicates the amount of energy that's released. So as the faults slip, that energy is going to go through the ground and hit up on the surface. And so the more energy it releases, the more potential damage there is. Okay. For earthquakes higher than 7.0, the Richter scale isn't super accurate. And so there's this other scale known as the moment magnitude scale. And it's just used for these really, really big earthquakes. They're pretty rare though. Okay. And then finally, we can talk about the intensity of an earthquake, and that refers to how much damage there was. So if an earthquake hits in an unpopulated area, there's not going to be a lot of building damage, and so we really wouldn't talk about it being intense. If it damages the ground, obviously that's going to be pretty intense, but we really refer to the damage it does for the intensity of an earthquake. All right, so what are the hazards of earthquakes? An earthquake can cause a landslide. It can actually cause this thing known as liquefaction. And so as the ground is shaking, sometimes what it does is it brings a lot of water up to the surface, and it liquefies the soil. It causes the soil to kind of instantly turn into mud, and that could cause mudslides. Sometimes large chunks of land will just break off of a mountain, and that's a landslide. Tsunamis occur when an earthquake happens out on the ocean floor. That energy then goes through the water, and it can create these tidal waves. Okay. Buildings can collapse depending on how strong it is, the earthquake is, and depending on how strong the buildings are. Fires are a very, very common hazard with earthquakes because gas lines might break, and then the gas is leaking, and all it takes is a spark to ignite that. Okay. Earthquakes cannot be predicted. Geologists and seismologists are working on that, and they're working on kind of early warning systems. It takes time for an earthquake to travel. So once an earthquake happens in one location, you can potentially get a 30 to 60 second heads up, like, hey, there's an earthquake coming. And that could make a difference because if you can get under a table and protect yourself, nothing's going to fall on you. We know what regions are at high risk of earthquakes simply based on the location of those plate boundaries and faults, but we cannot predict exactly when one will happen. There is some truth to the longer you go without an earthquake, the more likely it is for an earthquake to happen, because remember that stress is building up. Okay. And if these rocks are being pulled apart and they're stretching, they can only withstand that energy so long until they break. And then that energy is released as an earthquake. Okay. So again, look at that little picture there, drop cover and hold on. That's the best advice for earthquake safety. I grew up being told to get into a doorway and kind of bracing yourself in the doorway, because that tended to be the strongest part of the construction of the house. But really, we're definitely looking more for good, solid pieces of furniture to get under, because you can get under there faster. And that's how you can stay safe in an earthquake. If you can get outside away from power lines and trees and things like that, that's a good thing to do too. But watch out for those power lines, okay? All right, you guys, I think that's it. See you later.